Sasha Mikhailov and Jinping Wang. And I will try to develop to present a set of conditions which are necessary for the integrability of a given partial difference equation. So I will start with giving some definitions of dynamical variables, symmetries, and conservation laws, and then I will just develop all these. I will give the general formulation of integrability conditions, and in particular, I will focus on first and second order integrability conditions, and for which we know some examples. First order integrability conditions are the ones that all the ABS equations satisfy, for instance, and for the second order integrability conditions, I will focus on these three equations. The last one here is the equation that proposed recently by Adler as a discrete analog of the J-K equation. The first equation here, the equation for the variable u, is appeared recently in my work with Sasha Mikhailov, where we studied these second order integrability conditions. And the second equation, the equation for V, is a new equation which I found it recently and is related to the first one by Muir transformation, but I will talk about them a little bit later. Now let me first start with fix some of the notation that I will use. In this talk I will use n and m as the independent variables, and for the function u I will use its dependence on and its shifts. I will use this index notation with integer indices p and q, and I will denote the shift operators in the n and the m direction by s and t respectively. Now, in this talk, I will consider autonomous equations, quadrilateral ones, like this one. So in general, I will just use this letter q to denote my my equation. And here I will assume that q is a polynomial which depends explicitly on these four variables, on these four shifts of u, and also it is irreducible. It cannot be factorized in a product of polynomials depending on less than four variables. Here in my talk, as actually in once as I said, and actually it was the definition that also Sasha mentioned yesterday, by integrability of a difference equation, we understand the existence of an infinite hierarchy of symmetries. And so what I will try to do is that just to develop all these necessary conditions which guarantee, according to this definition, that my equation is integrable. Now, in the theory of partial difference equations, all the shifts of u are actually can be treated as variables, and so we can denote all these shifts of u as all the set of these variables by the capital letter U. Now, since we are dealing with quadrilateral equations, we can always use our equation here, q equals 0, and then we can try and we can use the equation to eliminate all the double shifts of u, and then just reduce any rational expression which can be restricted on solutions of our equation. Restricted on solutions of our equation means that the denominators do not vanish on solution of our equations. So any rational expression can be can be reduced to an expression involving only variables u l naught and u naught l, and we call these variables as we refer to these variables as dynamical variables, and we will denote the corresponding sets as us, ut, and u naught, which is the union of these two sets. And since our symmetries and conservation laws that we will deal with are rational functions of these variables, we will denote, just for simplicity, these fields of rational functions by fs, ft, and f naught respectively. Now, just two more definitions. A symmetry K of an equation Q is an element of this field F naught. So the function K here depends only on dynamical variables, which satisfies this equation here, modulo our equation and its shifts. And for quadrilateral equations, can be easily proven that always the symmetry splits into two parts, one horizontal and one vertical. So one part of the symmetry always depends only on dynamical variables in the horizontal direction, and the other part, kt, depends on dynamical variables only on the vertical direction. These allow us to make an answer and a working assumption that we will try to find only symmetries in one direction and or in the other direction. And okay, this is not the most general. This is not full in full generality, because there are equations which admit symmetries which. Well, let me put it this way. This does not mean that this splitting does not mean that Ks and Kt are symmetries of the equation, because there are equations which admit such symmetries, but each factor is not a symmetry on its own. Okay, but nevertheless, we will try to find symmetries only in one direction, Ks, and symmetries in the other, conditions for the existence of symmetries in one or the other lattice direction. And because we will also make some contact with differential difference equations, we may also consider, may think a symmetry Ks, this flow which commutes with the equation. That was actually this definition of symmetry was used yesterday in the talk of Dmitry. Now, for a conservation law, because in this derivation of integrability conditions, we will not find only conditions for the existence of symmetries, but also we will find conservation laws. These conservation laws come naturally from these conditions. Is a pair of functions rho and sigma for which satisfy this relation here, modulo again our equation. Here I didn't put the definition of a trivial conservation law, which is when this relation holds identically, which means that rho and sigma are the gradient of a function of this linear space here. Now, since our definition of integrability involves the existence of infinite hierarchy of symmetries, it would be very useful to have a way to just generate this hierarchy. So that would be useful to find an operator which maps symmetries to symmetries. And this operator usually referred to as a recursion operator, and the definition for this operator is this one, which is a pseudo-difference operator, such that it maps from this intersection of the domain of the operator and the linear space of symmetries to the linear space of symmetries of the difference equation. So that means that whenever the action of this operator is defined on an element of an element of this space KQ, of the linear space of the symmetries, then Rk will also belong in the same space, so it will be another symmetry. As an example of a pseudo-difference operator, here is the recursion operator for H1. And this is pseudo-difference because it involves this inverse operator, S minus 1, the shift operator minus the inverse of this operator. And if we try to write it out explicitly, then unfortunately we will have a formal, an infinite series of negative powers of the shift operator S. So so if we do so, we will have a formal Lorentz series of, in the previous case of order 1. In general, a formal Lorentz series of order n is a semi-infinite sum of this form. Here the coefficients an, a naught, a minus, and so on are elements in general of our field f node, and the leading term here an is not 0. Yes.
Then it seems to me that you get only s minus 1 in this form.
No, the leading term will be, the first term will be s. It will be a series of the form, well. So then you have a constant term, and then...
No, he asked about s minus 1 minus 1. So if you expand in a Lorentz series, you have infinite.
Yes, because
Parameter there.
Expand around 0 and
This parameter.
yes, so that is
you look at the space parameter and then this is some kind of difference replacing the derivatives. So
You see?
Okay. And actually, the important observation here is that if we have a pseudo-difference operator, we can always represent it uniquely by its Lorentz formal series. And this is important because when we will derive this, when we will try to derive these integrability conditions, we will replace every operator by their formal series. And here we have to make one important observation which differs from the continuous case. In the difference case, if we have a Lorentz series of nth order like this, A, N, we cannot always find a formal series of first order like this, BL, such that the nth power of the B series to be exactly the A series. So this we cannot always find in a closed a series like this, where Bi are elements of F naught, such that this relation holds. This in the continuous case, this is always possible, but here this is not always possible. So we have to every time to consider different order for our formal series, and I will explain a little bit later. Now, as I said, in our derivations, we will replace all the operators with their formal series, and that will allow us not only to derive the symmetries, but also the conservation laws, some hierarchy of canonical conservation laws for our difference equations. For this, we need to define the residues and of formal series. So if we have an nth order formal series of this form, AL, and I will denote always the formal series by this subbit L, then we define the residue of L as the constant term, A naught, the term which does not involve the shift operator, and the logarithmic term, the logarithmic residue, as the logarithm of the leading term of this formal series, the logarithm of AN. And now, and actually these two quantities will be involved in the conservation laws, will be actually involved in, will give us conserved densities. And because also in these derivations of integrability conditions, we will have to evaluate to find some commutators of operators, then we would need the residue of the commutator of two operators. And this the residue of the commutator is given by this formula here, where this function sigma is written here explicitly. And this is the difference analog of Adler's theorem for the continuous case. And these two relations here will be used later. Now, this is the main theorem. Suppose that we have a quadrilateral equation Q equals 0. Then there exist two pseudo-difference operators R and P of order n, such that this relation holds. If this is true, then the operator or R here is a recursion operator of the difference equation. Okay. And talk about integrability conditions. Now, this relation is valid if and only if this relation holds. Actually, we can rewrite this relation. We can find, deduce from this relation this one, where this operator phi here and its inverse are given from this relation. So it's completely, is explicitly, we can explicitly write it down, because it is determined by the derivatives of the polynomial Q here with respect to the shifts of U. And moreover, if this relation holds, then also the same relation holds if we consider powers of the operator R here. And actually, this is the set of our integrability conditions. These relations here will provide us with the integrability conditions that we are looking for. In particular, if now we have these conditions, we can, as I said, we can replace always these operators involved there by their formal series and just rewrite it in this way. Now, from this relation, we immediately can take the residues and construct in this way an infinite hierarchy of conservation laws. The first one is the logarithmic residue of our operator R, and the next one is just the residue of the different powers of our operator. So the first one, R1, will be just the coefficient R0. And here, for the operator phi with index L and its inverse are given here explicitly. So the coefficients A0, A1, A2, and beta naught, beta 1, and so on are given explicitly in terms of the derivatives of the function Q. So once we know our equation, and if we know also the recursion operator from these formulas here, we can immediately derive all a hierarchy of canonical conservation laws. Now, we have, this is our basic relation. We have an nth order, in general, recursion operator. We have these formulas for the operator phi L here and its inverse, and this is and this relation here actually provides us all the necessary integrability conditions for a quadrilateral equation Q equals 0 and a formal recursion operator of order n. And as I said previously, since in the discrete case we cannot always find a first order formal series, the nth power of which will give us this operator here, we have to go step by step. First, we have to consider operator R here of first order. If this equation satisfies the integrability conditions following for this first order operator, then we are done. We know that this equation is integrable, and the examples of such equations are the ABS equations or the equations studied recently by Gary Fulin and Yamilov. If not, then you have to consider second order recursion operator, formal recursion operator, and so on and so forth. And this is a general formula for the nth order recursion operator. In every step, the right-hand side is always known. Starting from here, we know beta naught here. It's given from the it comes from the operator from the inverse of the operator phi, and then once we know beta, we can find Rn. Then, in the next step, we know Rn from the previous step, and then and also know alphas and betas here, so we can find R with index n minus 1. And so on and so forth. So we can find in this way all the coefficients of the recursion of the formal recursion operator. And here we have to notice that the first integrability condition has already the form of conservation law, and the same holds true for the last one, which involves R naught. The integrability conditions in the middle do not have this form, but and the continuous case, it may happen these intermediate integrability conditions are just trivial conservation laws, are satisfied automatically, or provide us with non-local conservation laws. But in the discrete case, it seems that all these conditions provide us with non-local conservation laws. And for the case of a first-order recursion operator, all the integrability conditions have this form. Have the form of conservation laws, and they can easily be checked. But if we go to the second order integrability conditions, then the first here I just wrote the first three integrability conditions. The first and the third integrability conditions have indeed the form of a conservation law, but the second one does not have such a form. In fact, this second integrability condition is related to a non-local conservation law. And the theorem here states that if our equation does not satisfy the first order integrability conditions, but satisfy the second order integrability conditions, then there exists no first order formal series such that this relation holds. And moreover, this pair, rho 1 and sigma 1, is a non-local conservation law for our equation. And here the potential of this auxiliary function W satisfies this system. Okay, and now I will focus on these second-order integrability conditions and just discuss these equations which I showed in my first transparency. The first, all these equations are, it can be easily checked that they are not linearizable by point transformations. They do not admit first integrals. They are integrable in the sense that.
What does it mean?
Sorry.
What does it mean that they do not admit first integrals?
There are no functions, say rho of inner nodes, such that modulo the equation. Pseudo-constants, or in other terminology. Or for well, this first integral comes from the terminology for ordinary difference equation. So yes.
This is not claim about conservation.
No. They admit, it says that you don't have such functions.
Conservation laws.
You have conservation laws, the ones that I presented previously. Yes, they do have such conservation laws, but not say conservation laws of this form. And well, these equations are integrable in the sense that they satisfy the second-order integrability conditions, and because of that, they have infinite hierarchy of canonical conservation laws, and admit like pairs given in terms of 3×3 matrices. For the first equation, which I will mainly discuss here, well, it's a result of a small classification problem that we had considered. And it turned out that the only equation which survived from this class, the small class of equation, was this one over the top equation for U. Claude Vialet told me that he checked the algebraic entropy of this, studied this equation, and the algebraic entropy vanishes, which is another indication of integrability. And well, there are some relations among these equations. The first equation can be seen as a degeneration of the second one, of Adler's equation for this W equation, and the third one is related to the first one by a Miura transformation. But let me first present the integrability properties of the first equation. Here is the Lax pair, which is of this form. Well, I just forgot to say something about this equation. This equation actually appeared earlier in a paper of Raphael Boll, where he studied these 3D consistent equations. Is equation D2, I think, yes, right? Yes, D2, and when we're in Norway, I asked him about this equation. He told me definitely it is 3D consistent in this wider sense that we have, in principle, 6 different equations around the cube. And my question was if you can derive a 2×2 Lax pair then from there. And he told me that he will look at it, and he did, and he gave me the answer these days. And he told me that, okay, you can derive a 2×2 Lax pair, but it's a weak Lax pair in the sense of Hidarinda and Vialet, that this the compatibility condition is satisfied trivially, immediately, without any equation. So actually, you cannot derive a 2×2 Lax pair, a strong Lax pair from this 3D consistency. And so we have this 3×3 now, Lax pair, which it works. And well, these are the point symmetries and the lower order conservation laws of these equations. Amazingly enough, this very simple equation involves in its symmetries and its conservation laws the cube roots of unity. But now let's go to the integrability conditions, the second order integrability conditions. This equation satisfies, as I said, the second order integrability conditions, and from there actually you can derive, for instance, these 2 first canonical conservation laws. And moreover, from the theorem that I showed previously, you can also derive a non-local conservation law, which is given here. Now, what about the symmetries? Also from the integrability conditions, we can find, as I said, the coefficients of the formal recursion operator, and then from there you can construct your symmetries. In this case, the first symmetry, I just wrote here, the first symmetry is given by this rational expression. But it was a nice observation that actually, if you just make this Miura transformation, the symmetry here, and actually the whole hierarchy of symmetry of this equation, will take this form, this polynomial simple form here, with B2, M2, and so with B and M. Actually, I just denoted the Bokovialensky lattices, which are very well-known integrable lattices. And although these two integrable lattices do not commute, their combination here, their generalization here, is an integrable lattice as well, which is quite exceptional property. And similar observations actually were made recently by Yander and Postnikov, and actually later Adler showed that these generalization of Bokovialensky lattices they presented in that paper with Postnikov are related to the symmetries of his analog of the JK equation. Now, the nice thing about this Muir transformation is that actually works not only with the symmetries but with the equation itself. In fact, if you just we start with our equation here for the UA equation, make this Muir transformation, then we will derive the following quadrilateral equation for V. This asymmetric equation actually belongs in the class of equations that Garifulin and Yamilov studied recently, and they classified, but in their paper, the authors just considered first-order integrability conditions. So that's why they couldn't find this equation. So it is in their class, but it satisfies higher-order integrability conditions. And just to just to say what is going on with the other symmetry, because here the Muir transformation involves all these shifts in the horizontal lattice direction, and it's quite strange. It's quite important to see what's going on with the other symmetry. It turns out that the other symmetry, the other lattice direction, can be actually written in an explicit form, in a closed form. And since I mentioned also that there is a relation between the equation that we had found and Adler's equation here, that the generation is given by this relation here. If we just said in the equation here, W and C, if we make these changes, that the equation will take this form, and then, since this is an exact form, we can divide by epsilon, take the limit epsilon to 0. Actually, we will end up with this leading term, which actually is this equation. And this is the relation between these two equations. So, just to conclude, we derived and we gave the general formulation of the integrability conditions for difference equations, for quadrilateral difference equations. We presented, in particular, first-order and second-order integrability conditions, and we showed three equations which satisfy these second-order integrability conditions. And among these derivations, we found a generalization of the Bokovialensky lattices, which is given like here. Now, it will be interesting, in general, just to consider classification problems for equations, for quadrilateral equations which admit symmetries higher than -1, 1, like these equations here which admit symmetries -2, 2. And also, because now we have more examples of differential difference equations which involves of this form, it would be interesting to consider the classification problem for these equations. The only known classification for such equations is when this function f here does not depend on u2 and u minus 2. Thank you very much.
Questions, please. Does the distinction between first and second order integrability conditions maybe have some continuous analog?
Well, in the continuous case, you see, you can always use first order integrability conditions. Because there, in the continuous case, you can always find the nth root of an nth order operator. And in that case, some of the integrability conditions may be trivial conservation laws, or some you have to introduce some extra potentials, so non-local conservation laws and so forth. But in this case, in the discrete case, you cannot avoid it. You have to start with the first order integrability conditions, check the first one. If it is satisfied, then go on and check the remaining first order integrability conditions. If not, go to the second order integrability conditions. So you have to do it step by step.
More questions? I would have a question. So obviously there is two distinctive features of these equations. They do not satisfy first order integrability.
Yes, exactly.
And they do not have like pairs of matrices.
Exactly.
Do you have some explanation of this? What is the relation between these two properties?
At the moment, I cannot. I don't have an explanation at the moment. This is a question which I have also in mind.
More questions? Okay, then let's end this.